Many people have sketched out ways to put boots on Mars or establish a research outpost. But what holds us back is really the absence of a long-term strategy. For any proposed strategy, two hurdles must be cleared. First, the plan must meet a high absolute standard of technical, economic, and operational merit. Second, our institutions must possess the decision-making capability, capacity to recognize that merit. In other words, they have to separate signal from noise, they have to resist bias, that kind of thing. Let's take a look at how humanity has done so far. We've already encountered an era where civilization extends beyond Earth and out into the solar system. For 6 entire continents, we've gone through all the main developmental stages: explore, outpost, develop, settle, and celebrate. Celebrate means the territory has become consequential, made its own contribution. That is, it has added to human civilization in a noteworthy way. For example, why do we celebrate Australia and New Zealand? Australia and New Zealand reached the celebrate phase quite recently. These are some ways that they've contributed to uplifting our civilization. For example, they got a Nobel Prize for penicillin mass production. They invented a cochlear implant. They've invented ultrasound imaging. And New Zealand was the inventor of disposable hypodermic syringes and childcare safety seats. And they pioneered women's suffrage, the ability of women to vote. And Sir Edmund Hillary was the first to summit Mount Everest in 1953. He was from New Zealand as well. We've already largely incorporated near-Earth space into our civilization. Technologies such as GPS, communication satellites, and the discoveries made with space telescopes have already made Earth orbit a celebrated addition to human civilization. The next territories are likely to be the Moon and Mars, although I'm quietly holding out hope for a settlement in Venus's upper atmosphere as well. But this chart presents a very linear perspective. Looking at this graphic, you might expect that we'll industrialize the Moon in 100 years or so, and maybe settle Mars another 100 years after that. As Peter Diamandis said, our brains are wired for linear thinking in an exponential world, and it's causing us a great deal of strife. If we want to apply exponential thinking to analyze the pace of humanity's expansion, then we could plot time on a log scale. Then it becomes apparent that we're actually expanding faster and faster over time. From this perspective, it seems more reasonable to anticipate a settlement on the Moon by 2032, and perhaps a settlement on Mars by 2050. It's also worth noting that we didn't always use the same technology as we expanded from continent to continent and then on out into space. We evolved new abilities and invented new technologies along the way. Each was radically different from the one that came before it. This is what enabled us to expand outwards. Let's take a closer look at this last one, lunar orbit rendezvous.
Well, Mr. Dolan, this is certainly a very interesting idea. Why don't you let us think about it?
Well, I've prepared a report.
Oh, I have everything I need right here, Mr. Dolan. Thank you for your time.
Chances are, lunar orbit rendezvous would probably have ended up as nothing more than a footnote in the history of space exploration if a report on the idea hadn't landed on the desk of a NASA engineer by the name of John Hubble. When he first started reading the report, Hubble had the same reaction others did. Lunar orbit rendezvous seemed like just another far-fetched scheme. But the more he read, the more the idea made sense. By the time John Hubble finished the report, he knew. This was it. This was how you get to the Moon.
It's too great a leap for most people to buy into a strategy that goes straight from boots on Mars to Mars is a celebrated addition to the human civilization. So let's take a look at what some of the intermediate stages could be. On the top of this table, we have the stage, the value proposition, some blockers, and key enablers. The rows of this table are examples of stages, showing more specifically how we might progress incrementally. The first stage is probably boots on Mars. It's driven by geopolitical one-upmanship, and the desire for a nation or an alliance to grow its circle of friends so that it can accelerate progress through networking effects. The second stage is a research outpost. It's likely to inspire youth and make lots of talented people more excited and thus more productive in a variety of fields. As Mars seems to grow a little closer and become more accessible, some of the world's nations' expansionist drive will be redirected towards it. I'm not above using a classic meme to drive a point home. I attended an online British Interplanetary Society presentation last Monday and learned that Frank White, author of The Overview Effect, expressed a very similar idea in his book. He said war and space exploration may be mutually exclusive, because if one occurs at a massive scale, the other probably will not. Eventually, Mars will develop one or more keystone industries. Likely this will involve manufacturing products for use in space, since launching from Mars will be cheaper and easier than launching from Earth, thanks to its thin atmosphere, its high mountains, and shallower gravity well. Or it could be something like developing the best cancer treatment technologies or the best recycling technologies. Mars will have some advantages over Earth as well, such as fewer regulatory burdens, infrastructure that's lighter and lasts longer, fewer natural disasters, many readily accessible materials, and much higher speed limits. Eventually, I have no doubt, Mars will find its stride and start contributing celebrated accomplishments to human civilization. Now, in the blockers column, I've captured some reasons things might not go according to plan. And in the last column, I captured some of the key enablers, many of which involve reducing the cost of space transportation to and from Mars. The key takeaways here are that the earlier stages in the plan are prerequisites to the later stages, but belief in the later stages spurs on earlier stage efforts. Some of the key enablers are lowering the cost of two-way interplanetary travel, reducing transit times, and increasing safety. And these key enablers are critical to the economics of all the stages. Now, whether we aim to develop a sound long-term strategy or simply recognize one, we need to start with the basics. And the most basic thing is the orbital dynamics of interplanetary space travel. Distances in the solar system are vast, but distance is not always the best, or at least the only, metric that should be considered when the journey involves orbital mechanics. Delta V is a more commonly used metric for this kind of travel, as evidenced by the large number of delta V maps of the solar system that can be found online. But delta V maps are a bit like subway maps. They explain how the stations are interconnected, but they aren't a very accurate visual representation of reality. I reorganized the numbers from a delta V map to make this stacked bar chart, which I think better communicates how much additional delta V is needed to get to the moon and the surface of various planets in the solar system. In this chart, you can see that it takes roughly 50% more delta V to get to the surface of the moon or Mars than it takes just to get into orbit around Earth. The return trip, even with air braking, increases the delta V requirement significantly. Now you need on the order of double the delta V that you need to get into low Earth orbit. Unfortunately, these charts are another example of linear thinking in an exponential world. They are highly misleading. To understand why they're misleading, I need to explain cost versus delta V. Now, it's possible to place points in this chart using information from a variety of sources, but let me first go over what the axes in the chart are. The horizontal axis is delta V. In other words, how much velocity change do you need to get from where you are to your intended destination. And the vertical axis is the cost per kilogram at that delta V. Now, if you had a technology where the cost was linearly proportional to the delta V, then that technology would have this cost curve. If the technology had a relationship where the cost was proportional to the square of the delta V, then it would have this cost curve. It's still a straight line, but it's just steeper on this log-log chart. And if the technology was one where it was proportional to the velocity cubed, such that 10 times the velocity would require 1,000 times the cost, then you would have this straight line. It's just a steeper slope again. So these are some examples of cost curves for different technologies. Now, I'm going to plot some points in this chart, but I wanted to give you some idea of where they came from. There's a paper called Launch Cost versus Delta V, which you can find online by searching for it. And it gives you the methodology by which I calculated all these points from various missions that are in the public domain. So let's plot these points in the graph. So you'll see here that on the low end of the graph, we have commercial, the cost of placing something in low Earth orbit, which is commercial costs. These purple triangles are a variety of Falcon Heavy reusable missions. Then we have the ISS round trip from ISS resupply data, the Moon low orbit, Moon surface, Mars 2020, that's Perseverance and Ingenuity, the Apollo program's costs, and Mars sample return, which is the highest cost of all. You can see that the cost goes up significantly with delta V. If you plot a line, or if you fit a line to this data, then you get an exponential fit, which is shown by this equation here. Now this makes sense, since the physics of the rocket equation say that there is an exponential relationship between the mass ratio and the delta V. Now the further away from the curve you are, on the down and to the right side over here, the better you're doing. This tiny little triangle down here is an example of a partially reusable Falcon Heavy mission. It's a little bit better than average because it's down and to the right of the line. This is what the Europa mission would have cost if it had launched with SLS. Just a little bit better still than the Falcon Heavy mission, or the Falcon Heavy reusable mission. Finally, this is what the Europa mission with the expendable Falcon Heavy cost. It's a little bit better still than the SLS. Now NASA got a really good deal on its expendable Falcon Heavy flight. I think this might have been because the side boosters have been reflown several times already, and maybe because SpaceX thought it would be a good idea to beat SLS in a head-to-head competition. If they lost to SLS in a fair fight, a lot of reporters would have dug into the math to try to understand why, and they would have understood the relationship between cost and delta V as a result. The point is that most people tend to think about these things in a very linear fashion, and they arrive at the incorrect conclusion that the SLS is something that's like 5 or 10 times more expensive than Falcon Heavy. They're ignoring the fact that delta V is very expensive, and SLS is competitively priced because it delivers a lot more delta V. Now we can use this curve to obtain ground truth information on roughly what the one-way and round-trip cost per kilogram is to the surface of Mars. The one-way trip is about 4 million per kilogram, and the round trip is about 2.5 billion. We can use those numbers to estimate what it will cost to sustain a human presence on Mars for, say, 20 years. I assumed 10 Mars transfer windows, 4 crew per window, 80 kilograms per person, and 300 kilograms for ECLS, or environmental control and life support and provisions. Now this 300 kilograms is really low, but I'm just trying to illustrate a point. And finally, I assumed 450 metric tons for a Mars base, which is the same mass as the ISS. Now the round trip part of that mission ends up costing $38 trillion. And the one-way part, basically delivering the base, is 1.8 trillion, total of 39.8 trillion. What we discover from this thought exercise is that the round trip part dominates, being $38 trillion. The one-way part is far, far cheaper. So one solution, of course, is to build infrastructure on Mars, specifically a propellant plant that would refuel your rockets so that the crews can come home. Now, if we do that, we can reduce the cost to $2.7 trillion for this space program. Another solution is to try to select people who are willing to stay on Mars and make babies. But then you just have to keep sending more and more stuff to Mars until eventually you have a small village and then a city. Of course, if you propose that to Congress, they're going to think it's a trap. It would be a lot easier to convince Congress, taxpayers, and our partners in space exploration if we could come up with a game-changing idea, like the Lunar Orbital Rendezvous idea that helped make the Apollo program easier. An idea that changes the economics so fundamentally that these interplanetary journeys, and thus the whole Mars strategy, becomes far more affordable. We've already established that infrastructure on Mars, specifically a propellant plant of some kind, is a good idea. Gerard O'Neill helped to establish another kind of infrastructure. A mass driver on the moon is also a good idea. He and his collaborators even developed some prototypes. From an energy perspective, we can see one of the advantages that a mass driver has over rockets. This orange line represents the power per kilogram versus time for the Falcon 9 rocket. So this is the first stage, and then this is the second stage burn. The blue curve represents the power that a mass driver needs to accomplish the same thing. Obviously, it's a lot less. If you factor in the electricity to propellant conversion efficiency and the difficulty of finding feedstock for a propellant plant on the moon, it's not hard to see why O'Neill baked a mass driver into his plans. Now, if a mass driver on the moon is a good idea, how would a mass driver on Mars? Mars's gravity is only a little bit higher than the moon's, so you only need to accelerate a little bit faster to reach its escape velocity. Mars's atmosphere is as thin as it is on Earth up where the spacecraft re-enter, so aerodynamic heating on the spacecraft should be manageable. Mars also has some really tall mountains, which are great for redirecting a mass driver launched spacecraft skywards. And a mass driver would convert that electricity into kinetic energy much more efficiently than a propellant plant and a rocket would. So perhaps a mass driver on Mars should be part of any long-term plan for Mars, just like it's a fundamental building block of O'Neill's plans to build space settlements out at L5. Okay, but talking about infrastructure on the moon and Mars seems like the far future. Well, the infrastructure itself may seem that way, but talking about it now is relevant to the overall story of how Mars will one day become a celebrated addition, or a celebrated jewel in the crown of human civilization. Let's talk about the more immediate problem, though. Getting to Mars is too expensive. We need to change that. We need the equivalent of the Apollo Lunar Orbital Rendezvous breakthrough. Remember at the beginning of this presentation, I said that there were two requirements. First, that a strategy must meet a high absolute standard of technical, economic, and operational merit. And second, our institutions must possess the decision-making capacity to recognize that merit, separating signal from noise and all that. Well, recently, Jeff Thornburg shared his thoughts on the present situation on Neil deGrasse Tyson's Star Talk.
We don't have enough integrity in the business right now, is a personal observation. Because the push to make money, the push to grow a business and satisfy investors sometimes compromises people's value systems in ways that aren't great.
We heard Robert Zubrin say this morning during his keynote that he thinks that, he has every confidence that Starship will eventually get to orbit, he said. But he thinks Elon's prediction that Starship will be able to place 100 tons in orbit is altogether another thing entirely. I think those were his words. Let's hear what Jeff's thoughts are on that.
Where exactly does a lack of integrity hurt the business and then subsequently?
I think lying about the progress of your product. That's where
to keep the money coming.
That's where I see it the most.
I see.
Vaporware.
Businesses are trying to drive for that next fundraise, that next investor, and they lie their asses off to get to the next step.
Okay.
And that's where I see it the most.
Vaporware.
By the way, if you want a good perspective on Starship, I thought that this article published by the Scientific American was a pretty good example of high journalistic integrity. Now, can we extend the idea of a mass driver on the moon or on Mars to Earth? Well, this is an idea that is not widely accepted yet, but let's take a closer look at it. First, I'd like to bring your attention to this video that was just released this morning. I really hope that you'll watch it right through, give it a like, subscribe to Brad's channel, and post a comment so that the algorithm will suggest the video to more people. It goes into a lot more detail than I have time for today. The video goes over some of the reasons why earlier mass driver concepts didn't gain traction, and talks about what's changed since then. And it explains the technology that I've been involved in developing called variable pitch screw launch. This is a rendering of what a mass driver on Earth might look like. It's basically a long evacuated tube with airlocks at each end. And in the first section, the spacecraft accelerates. Then it goes up a ramp, which points it skywards. That ramp will be on the side of a mountain or maybe just under the surface of the side of a mountain. And then it coasts inside an elevated evacuated tube to get above the densest part of the atmosphere without any aerodynamic drag. And finally, it powers its way through the rarefied upper atmosphere and then out into space. This concept has been implemented as a digital twin, and this is a capture from the digital twin. But keep in mind that I exaggerated the size of the tube and the spacecraft, and I also sped up the simulation here by 5x, just so that it wouldn't take so long. By the way, the digital twin is available on GitHub, and it's about 27,000 lines of code right now. And it really is more than just a 3D rendering. The digital twin models the physics, the mechatronics, the orbital dynamics, and some of the economics of the technology. It has a full cost model that goes into the cost of materials, the size of the parts, and it tallies it all up and gives you a final cost for both the capital cost and the operational cost of this infrastructure. Now here you can see the vehicle is curving upwards on the ramp, and then now it's traveling through the elevated evacuated tube. And at the end of the tube, it breaks out through an airlock, like an airlock with fast doors and into the upper atmosphere. And it fires its rocket initially to get through the atmosphere to maintain its speed. But then it can coast from, once it's up at about 100 kilometers, it can start to just coast. And it's on its way to Mars. I presented the variable pitch screw launch concept, or VPSL, last year at the Electromagnetic Launch Conference in Amsterdam. And the paper that I submitted with that presentation passed peer review and was published on IEEE Explore in August of this year. It's a 23-page paper, so I'm not going to be able to go into a lot of detail here, but if you aspire to be the John Hubble of the 21st century, I'd encourage you to give it a read. But the core idea that I'd like to explain right now is that you can use infrastructure to fundamentally change the economics of interplanetary space travel. The paper explains how the cost of VPSL varies with its exit velocity. You see, where a rocket's cost scales with the exponent of delta V, the variable pitch screw launch cost scales with the square of delta V. Basically, its cost curve is a straight line down here. Now, earlier EML concepts such as StarTram had a cost curve that scaled with delta V cubed. Even though this was a better slope than rockets, they really couldn't compete where the market for launch was focused, which was the delta V that you need to get to low Earth orbit, right around here. And they didn't even try to compete at the delta Vs you need for interplanetary travel, which are up around here. Since, at that time, when they, like in 2000 to 2010, when they were developing these ideas, the market was pretty small still for going to the moon and Mars. Now, variable pitch screw launch is a technology with a better cost curve, where cost is proportional to velocity squared. That makes it kind of interesting for getting to Earth orbit, which is down here, but really very exciting for interplanetary travel, which is where this vertical line is. It's literally 3 orders of magnitude cheaper than rockets. And this is based on sound physics, which anybody who graduated from high school can understand. Not based on promises to make things cheaper by being clever at reentry than the guys who built the space shuttle, or better at math and accounting than the guys at JPL who figured out that Mars sample return was going to be a multi-billion-dollar flagship program. I think that if you can understand why it's possible to make infrastructure with a V-squared cost curve when rockets have an exponential cost curve, then you're probably primed to dig into the rest of the story. Now, to make the case that variable pitch screw launch is technically and economically viable, we created something called an evidence ledger. Basically, this is a list of claims, all of which need to be true in order for the overall concept to be valid. And you can see there's a lot of claims. Now, our plan is to put these claims online using a custom evidence ledger application that we created, and then encourage experts in the field to go over the evidence we present, write a review, and indicate whether or not they believe that the claim is valid. We're hoping that this methodology can also be used by others to improve our decision-making capacity as a nation. And the Mars Society Technology Institute plans to add this to its suite of tools that it provides to startups to help them make their business case to investors. But this is something that we'd like all of you to participate in. So please see me afterwards so that I can add your name to our list of subject matter expert reviewers. Okay, in conclusion, tactics are not enough. We need a long-term strategy. And the long-term strategy generates pull for the first stages in our strategy. The high cost of rockets kills efforts to develop a viable long-term strategy. And in the past, when we expanded, we did use different technologies along the way. Like we went from walking to ships, to steamships, to rockets. Now, rockets have a cost that scales exponentially, and you just saw that's a very aggressive cost scaling. Most electromagnetic launchers scale better with V cubed, but that's still not good enough because of the high infrastructure cost. It would be good enough if we had a lot more demand for launch. I think then the traditional kinds of electromagnetic launchers could compete against rockets, but at the level of demand we have right now, they can't compete. Variable pitch screw launch is a breakthrough because it scales with velocity squared instead of velocity cubed. It can also be human rated, and it significantly lowers the cost of travel to Mars specifically, or the moon. It can also lower the cost of returning from Mars to Earth if you built a variable pitch screw launcher on Mars. And that can enable the overall long-term strategy by solving that problem of two-way interplanetary transportation. Now, you can help by becoming a reviewer or possibly by being the next John Hubble, who finds the breakthrough idea that changes the whole ballgame. Thanks very much. Any questions?